So welcome to this week's Shear Flow Instability Transition seminar, which is a joint seminar with the Australian Fluids people. So we're very lucky this week to have Yury Kachanov, one of the few people in the world capable of doing careful transition experiments from the Khristianovich Institute in Novosibirsk. Yury, over to you.
Okay. Thank you very much, Phil, for introduction and for the invitation to take part in this seminar. It's a pleasure for me. I want to say that, in fact, I'm not the only co-author of this talk, because I will show a lot of results obtained together with my younger colleagues, Vladimir Borodulin, Andrei Ivanov, and Dmitry Mishchenko. And also, I will show many other results obtained jointly with other scientists from different countries, Jeffrey Crouch and Liang Ge from Boeing, Werner Wills from Stuttgart University, Rames Orlu and Artishil Hanifi from Stockholm Royal Institute of Technology, Stefan Hein from DLR Göttingen, and with others also Russian, my younger colleagues. So I'm glad that this seminar is joined with the Australian Fluid Mechanics seminars. But I'm not from Australia, but I'm from Siberia. This is also quite interesting place, and I will show this picture just you to see what we had 5 days ago. This is huge heap of snow just removed from the yard, which started melting yesterday or 2 days ago. And the same place in spring looks like this. So this is just snow. And the most important object in this picture is my car standing under the snow here and just in the yard. So let me start with a brief introduction. We all flew and fly on arrow-shaped wings. And I just show as an example here a row of Russian airplanes produced in different years from 1950s till present days. And it's well known that if you look at components of total drag of modern long-range subsonic passenger aircraft, then we will see that nearly 1/2 of this drag is viscous drag, associated with presence of boundary layer and skin friction. Therefore, the viscous drag reduction problem is of great importance, and for fuel economy and for improvement of aerodynamic quality of airplanes. So I want to show also this classical graph. Skin friction coefficient versus Reynolds number for flat plate. Upper curve correspond to turbulent flow, lower to vice versa. Yes, to turbulent flow, and lower corresponds to laminar flow. Modern airplanes fly approximately at such large Reynolds numbers. And here, for large airplanes, difference between turbulent and laminar friction is more than 1 order of magnitude, very significant difference. It remains large even for small airplanes and gliders. If we look at the boundary layer, if we will go from leading edge downstream, then initially the flow usually is laminar. Then we have transition to turbulent flow and friction increases dramatically. If we are able to postpone transition to make it like this, then in a certain Reynolds number range, we have so-called laminarization, and the friction is reduced dramatically, very much. This partly is already achieved for small airplanes and gliders. So they have laminar flow around significant part of their surface, and due to this circumstance, the skin friction is very low. Prior to start main part of my talk, I want to make three remarks. First, I will concentrate on low-speed subsonic flows, which have been studied very much better at present than transonic flows. Then second, I will present you a viewpoint of an experimentalist, basically, and concentrate on experimental results. And third, I will skip a lot of very important early experimental studies, which are well known and have been described in great number of books and review papers. And I will concentrate on a relatively recent data obtained during past years. So swept wind boundary layer has several kinds of instabilities, which I will try to describe now. So this is actually what is swept wind. Swept wind is an idealized arrow-shaped wind. Idealized in the sense that nothing depends on it on span-wise coordinate. This is plan view. So all geometrical parameters are the same in span-wise direction. And also potential flow has a very special property. If we decompose velocity vector into two components, the component, span-wise component, which is parallel to the leading edge, is constant everywhere in the whole flow field, excluding viscous boundary layer. And this constancy is often called the sweep condition. Sweep condition is satisfied for infinite span swept wind. The sweep angle is high. Another component which is perpendicular to the leading edge is of course not constant. It accelerates, the flow accelerates initially, then decelerates. And therefore, the shape of the streamline of the potential flow and viscid flow is curved, so-called S-shaped. And this curvature is produced by acting of pressure gradients, so forces associated with pressure gradient, which are shown here, these forces. The same forces act fluid particles which are inside boundary layer and have lower speed due to viscosity. But if the same force acts the particle with lower speed, the trajectory changes differently. And therefore, inside the boundary layer, the particle trajectory deviates from the trajectory outside. And this mismatch leads to appearance of so-called crossflow. The crossflow directed as shown here. This is in the vicinity of leading edge, and this is near trailing edge. Inside the boundary layer, we have mean velocity profile, which is rotating, I would say. The vector is rotating when we approach the wall. At the boundary layer edge, this is coordinate system with star, which is coupled with the velocity at the boundary layer edge. Is directed as shown here, then closer to the wall direction is changing. We can decompose it into the component in the direction of the potential flow and orthogonal component. The orthogonal component is the crossflow itself. And this profile has inflection point, and this is always a sign of additional instability. This flow in 3D or in this 3D boundary layer usually is more unstable compared to the corresponding 2D boundary layer. So there are several instabilities of this flow. First, when the flow just touch the leading edge, if the thickness of the aerofoil is large, then we have a boundary layer flowing along the leading edge. And this boundary layer can be unstable. And this instability is often called attachment line flow instability. Then further downstream, we have region of so-called favorable pressure gradient when velocity increases. Here, we can observe basically two kinds of instability, crossflow instability and streamwise curvature instability. Further downstream in the region of nearly zero pressure gradient, Tolman-Schlichten instability may occur. And closer to the trailing edge, we often have a competition between crossflow instability and Tolman-Schlichten instability. They both can play a significant role. But for so-called long laminar run airfoils, the region of favorable, so-called favorable pressure gradient is enlarged. The main goal is to suppress Tolman-Schlichten instability. But the same pressure gradient which suppresses Tolman-Schlichten instability leads to intensification of crossflow instability. The stronger the pressure gradient, the greater is this instability. And in my talk today, I will concentrate on this kind of instability, despite I'll touch also some Tolmie-Schlichting instability as well. So how the cross-flow instability modes look like? I will illustrate this on this picture. This is visualization obtained by infrared camera on 45 degrees web twin in our institute, in our group. And in case of low turbulence level, we have turbulent flow here, laminar here. We can see turbulent wedges. And the cross flow in this case is directed as shown here inside the boundary layer. And this arrow show local direction of the potential flow velocity vector. Stationary cross-flow instability modes, which also can be amplified with zero frequency modes, they usually have axis of vortices nearly parallel to the local direction of potential flow, but not exactly. They always deviate from it by approximately 2 degrees. But they also have traveling cross-flow instability modes, which can be also amplified by the instability mechanism. The most dangerous of them are indicated here. They exist in a range of propagation angles, and they propagate like shown here. So they propagate in the direction opposite to the cross-flow direction. And in fact, they approach the leading edge of the airfoil. There is another group of cross-flow waves, or unsteady cross-flow instability modes, which propagate in the direction of the cross-flow and towards the trailing edge of the airfoil. But this second group of traveling modes, cross-flow modes, the flow is less unstable with respect to this group. So it's not less dangerous usually. So how the cross-flow vortices look like, stationary ones. So this picture shows mean velocity disturbance measured in our experiments in the plane perpendicular to the wall and to the free stream direction. So the wall is here, and we can see regions of greater, so higher and lower mean velocity disturbance, values of mean velocity disturbance. And what is important that these cross-flow vortices represent counter-rotating vortices, which rotation is shown here by blue and brown arrows. Vortices A and B rotate in opposite directions. Some people believe that cross-flow vortices are co-rotating. This is not quite correct, because the vortices themselves are counter-rotating. And this is clearly shown in experiment and in calculations by Dillman, for instance, Arnal in 1980s. But after superposition of these counter-rotating cross-flow vortices with the base flow, which is three-dimensional, we have co-rotating vortices. So co-rotating vortices are not cross-flow vortices, but the flow composed of superposition of the base flow and counter-rotating cross-flow vortices. And in this case, a total velocity contours look like this. This is taken from one of DNS, as I remember, Markus Glocker from Stuttgart University. In 1990s, there was a great problem of description of initial stages of transition initiated by cross-flow instability modes. These are two examples from early experiments by Bipus and Müller and Radzetsky, Ribert, and Sarik. Red curves show experimental amplification curves, so distribution of amplitude in the chordwise direction. And other curves display theoretical results, linear stability series. We can see very significant mismatch of this data. And it looked like that the linear stability series are not applicable for description of initial stages of transition on swept twins. We started our experiments on the cross-flow instability in the end of 80s, and the majority of experiments were carried out in this wind tunnel of our institute in Novosibirsk, which is called T324. This is very good low turbulence wind tunnel. And this is our first experimental model. We accepted, we use the idea of Bill Sarek. Instead of real swept wing, we made swept plate, and the pressure gradient along this plate in the clockwise direction was induced by a contoured wall bump. And also we added side walls, which help us to diminish influence of the test section walls and to provide better satisfaction of this infinite swept wing condition, sweep condition. In first experiment, this is for a sweep angle of 25 degrees. In first experiment, side walls were absent. And then we designed another model for 35 degrees, very similar design. And we also measured very accurately the base flow and found that the sweep condition is very well satisfied in the middle of the, our model. This is illustrated by these two figures. One figure is for 25 degrees sweep angle, another for 35. Stream chordwise component of mean velocity at the boundary layer edge accelerates. So we have so-called favorable pressure gradient, the same for 35 degrees. But the spanwise component is practically constant. This is an indication of satisfaction of sweep condition. And we use different kinds of disturbance sources to perform controlled experiment. For investigation of stationary cross-flow instability modes, we use patches onto the surface, sticked onto the surface, either spanwise periodic or isolated. And we also use stationary blow-in or suction through streamwise elongated slots. But for investigation of non-stationary cross-flow modes, we use different kinds of disturbance sources. For example, several kinds of surface, circular surface vibrators, and also very good source we call it the universal source of oblique modes. So we were able to excite with this source even one oblique mode inclined at any angle to the flow direction, or several modes like this. And in recent experiments performed in Stockholm, we also use spanwise periodic rows of membranes, oscillating membranes. So the traveling modes in the first experiments we studied by means of our universal disturbance source and circular vibrators, and we obtained results which were compared with calculations by Jeffrey Crouch from Boeing. You can see here amplification rate versus spanwise wave number obtained for three different frequencies. And curves are results of calculations, linear stability theory. As you see, we have very good agreement within scattering of experimental points. We also studied all other stability characteristics, in particular dispersion characteristics. This is dependence of streamwise wave number versus spanwise wave number for three different frequencies. And this curve is extrapolation of our results to the zero frequency, and this curve corresponds to stationary crossflow vortices. And again, we can see not bad agreement between theory and experiment. So as a result, the applicability of linear crossflow instability theory to description of final stage of transition on swept winds was clearly shown in these experiments. But unfortunately, meanwhile, this paper was rejected from the GFM in 2002, although the results were obtained in 1995. And it was published only in proceedings of one of Russian conferences. But later, we repeated, we performed similar experiments, but not on a swept plate, but on a real swept wing. These experiments were carried out in the framework of European project RECEPT, Framework Program 7. In Stockholm, this is MTL low turbulence wind tunnel, where we make experiments. And this is our experimental model, which also equipped 35 degrees with airflow section. And it was equipped with side walls to provide better satisfaction of sweep condition. So again, we had very good base flow, and here you can see streamwise and spanwise velocity components measured at the boundary layer edge in the chordwise direction. We have good satisfaction of sweep condition and good agreement with the theoretical model. our theoreticians, basically Ardeshir Hanifi and Stefan Hein, performed calculations. The same is for the boundary layer. And as a result, we obtained perfect agreement between theory and experiment. I show here amplification curves, circles, and the stream-wise, chord-wise distribution of the phase of perturbations for two different span-wise wave numbers and one fixed frequency. And this is the same for another frequency, which is very low, actually 2 Hertz. And curves are calculations. Points are our experimental results. We have very good agreement between theory and experiment. And 2 Hertz is, we call it quasi-stationary regime, because the flow passes several times the whole region of our measurements during one cycle of oscillation. So in effect, these are crossroad vortices, very low frequency disturbances. But then when we change the angle of attack, we obtain conditions when Tolman shifting modes prevailed. And we performed again measurements on the same experimental airfoil, on the same model, real model with presence of surface curvature and everything. And we again obtained very good agreement. I show you this is for one of frequency, this agreement for several span-wise wave numbers, amplitude distributions in the chord-wise direction, and phase distribution versus chord-wise direction. And again, symbols are experiment and curves is a linear stability theory. The agreement, I would say, is perfect. Therefore, at present, the applicability of linear stability theory to description of initial stages of transition on real swept winds is fully substantiated for both the crossflow instability and for three-dimensional tone shifting instability. The next section of my talk is about mechanisms of excitation of instability modes. Such mechanisms are usually called receptivity mechanisms. So this is problem of receptivity of the base flow to external perturbations of different kind. This problem is very complicated, and this complexity is displayed by this table. So every column in this table is one of kinds of surface perturbations or the base flow. And every row also either the base flow or one of kinds of free stream perturbations like acoustic waves, free stream turbulence, or stationary vortices. Cross-section of every row and column correspond to one of possible receptivity mechanisms. For instance, this cell corresponds to scattering of acoustic waves on surface vibrations, and so on. You see, we have a lot of mechanisms, and if you want to predict, to calculate correctly the transition location, we must know which of these mechanisms are important, which are less important. And of course, the importance depends on the base flow characteristics and disturbance characteristics. So this is not a simple problem at all. And in our experiments, we investigated a lot of these mechanisms. I will illustrate these results for two cases. First case is receptivity to surface non-uniformities, either stationary or non-stationary, that means vibrations. We studied these investigations in the end of 1980s for stationary perturbations. We put some patches onto the surface, but it turned out, unfortunately, that the boundary layer response to these studied kinds of roughness turned out to be quadratic. That means nonlinear. And we were not able, of course, it was necessary to diminish amplitude of our roughness elements, but it was impossible because the accuracy of measurements at zero frequency is very poor, and we were not able to obtain results. Then we decided, it looks like again that we cannot find investigate linear receptivity problem and to check validity of the linear receptivity approaches. But we decided to do it differently. So we decided to replace our stationary disturbance sources by non-stationary ones. First of all, by surface vibrators. And then we studied receptivity with respect to non-stationary perturbations. And we have got quite good results. Here you can see initial spectrum of excited cross-flow instability waves versus span-wise wave number for a fixed frequency, and this is for another frequency. Experimental points and theoretical curve by Jeffrey Crouch from Boeing calculated. And we can see not bad agreement, especially in the regions where we have most dangerous cross-flow instability modes. These modes usually have span-wise wave numbers around 0.4, 0.5, 0.6. And then we found that the receptivity coefficient, which was defined as ratio of initial spectrum of disturbances divided by resonance spectrum of surface vibrations. And we found that this receptivity depends nearly linearly, it has linear dependence on frequency. And we extrapolated our data to the zero frequency and obtained in this way the receptivity coefficients for stationary modes, for steady surface roughness and stationary vortices. And the result we compared again with calculations by Jeffrey Crouch. And you can see here, here initial spectrum and here receptivity coefficients. And taking into account great complexity of obtaining this coefficient, which include extrapolation of data upstream to the position of the source, we think that this agreement is rather good. And this result shows that it was actually the first evidence of applicability of linear receptivity theory of a swept-in boundary layer to surface non-uniformities at excitation of cross-flow instability modes, both stationary and non-stationary. And this paper was published in JFM in 2002. Another case, a receptivity case also important, I want to show you, is receptivity to incident flow turbulence, which can scatter either on natural base flow non-uniformity or on surface roughness or on surface vibrations. So we studied all these cases, at least for the case of 25 degrees swept in and also 35 degree. And I just want to explain the formulation of the experimental problem. So we have a vortex street propagating along the boundary layer edge. And then these vortices interact, for instance, with the flow in the vicinity of the surface roughness. This is non-uniformity. And these vortices are transformed into cross-flow instability modes, which have, of course, the same frequency. Then we studied the case when the non-uniformity is non-stationary, when it oscillates at frequency of S. And in this case, scattering of free-stream vortices occurred, of course, at combination frequencies, F vortex plus minus F surface. And we also studied this problem. And one more interesting problem when the scattering occurs on natural non-uniformity of the base flow. This is already distributed vortex receptivity problem. The excitation occurs not in one point or in vicinity of a small vicinity of streamwise coordinates, but everywhere actually. And newly excited disturbances are superimposed with previously excited and so on. And we investigated this problem as well. As a result, we obtained for 25 and 35 degrees swept winds. We published 4 JFM papers and also some conference papers. And we are preparing for more papers, which will appear very soon. Unfortunately, I cannot describe all details of the results in this field. This is for additional talk. But what is interesting to analyze, to compare efficiency of two receptivity mechanisms. Surface receptivity amplitude coefficient is this, and surface vortex receptivity amplitude coefficient. So these coefficients are defined slightly differently. So for the case of surface vortex receptivity, with initial spectrum of excited disturbances, we divide by resonance spectrum of surface non-uniformities and by amplitude of free-stream vortex. So these coefficients are not comparable. But if we fix value of vortex, free-stream vortex, then we can compare these coefficients and to say which receptivity is stronger. We found that these two kinds of receptivity become comparable, receptivity coefficients, only at extremely high free-stream vortex amplitudes, around 50%. But at this vortex amplitude, hardly our linear receptivity mechanism is varied. So this is actually outside the region of validity of our approach. But if the free-stream vortex amplitude is weaker, like 15%, then we can see that the surface vortex receptivity is nearly always weaker than the receptivity to surface non-uniformities. And especially for lower vortex intensity, the surface vortex receptivity coefficient is even lower. So we can conclude after this analysis that in general, scattering or excitation of cross-flow instability modes by surface non-uniformities is more efficient than excitation of similar modes by free-stream vortices due to scattering on surface non-uniformities. So now let me say about scenarios of laminate turbulent transition. This is an important point. Initially, I will describe the case of low turbulence level. LTL means low turbulence level. So this is a picture of visualization by infrared camera obtained in our experiments for sweep angle of 45 degrees at low turbulence level case. I showed already this picture. So we have turbulent flow here, laminal here, turbulent wedges. The turbulence level is below 0.1%. Main features of this transition are the following transition scenario: presence of turbulent wedges, always, and absence of intermittency. We don't have any real intermittency in this case. How the transition occur? Actually, in almost, we always observe development and amplification of stationary vortices, cross-flow vortices, and then sudden rise of very high frequency perturbations, very rapid increase of the amplitude. This was observed in many experiments prior to us, in particular Kobayashi experiments and many others. But later, this was obtained also theoretically. This is from calculations by Malik, Chowdhury, and Chan in the end of 90s. They found this is contours of total mean velocity in the plane perpendicular to the wall and to the floor. You can see primary cross-flow vortices superimposed with the mean flow. And below you can see wall normal gradients from this picture and span-wise gradients of this picture. You can see that in some regions where the gradients are very large, high frequency disturbances are amplified. So red lines correspond to high frequency perturbations. They are sitting on the largest gradients in wall normal direction. And this was called Y mode of secondary instability. And for span-wise gradients, similar picture is observed. So some other high frequency disturbances are amplified in the regions of the largest span-wise gradient of primary flow. Similar results were obtained also in DNS. This is an example of Wasserman and Clocker. Similar pictures, and they found several kinds of high frequency secondary instability, always present in the regions of large gradients of primary cross flow, base mean velocity flow. Superimposed, this is superposition of primary cross flow modes and the base flow itself. Similar results were obtained in experiment. This is from experiments by White and Sarek, published in 2005. This is the primary flow composed of base flow and primary cross-flow vortices. And they found growth of high frequency disturbances, which were sitting, as it should be, on the largest gradients of the primary flow, spatial gradients. In the frequency spectrum, they observed rapid growth of peak or hump, rather broad, but not very much, of high frequency disturbances. And this corresponds to amplification of, to appearance of local high frequency secondary instability. Of course, we saw the same in our experiments. This is in one of them. And this peak in frequency spectrum correspond to quasi-sinusoidal oscillations in the time trace. It looks like, you know, our primary low frequency disturbances becomes heard. So very, very high frequency, like noise appear, but this is not noise, this is amplification of high frequency disturbances. And if we perform more detailed measurements of the fields of our perturbations, we see the following picture in this low turbulence level case. Shown here are isocontours of mean velocity disturbance, plane view. This is local direction of the flow if you look from above on our airfoil. And we can see formation of quite strong span-wise periodic perturbations with amplitudes something like 20–30%. And this picture show isosophisis of amplitudes of non-stationary perturbations. And you can see that in low turbulence level case, they are very weak. Their amplitude may be 4 or 5%, not more. However, at a certain stage, we observe appearance of high frequency perturbations. The third plot show isocontours, levels of amplitudes of high frequency disturbances. In this particular case, higher than between 500 and 1,800 hertz. So in this case, we have, this is beginning of formation of turbulent wedge. And at the tip of this wedge, first high frequency secondary instability appear. Now, but what is going on in case of enhanced turbulence level? By enhanced level, I assume the level higher than 0.1%, but below 1%. For example, in this case, 0.85%. Again, visualization by infrared camera of transition and at sweep angle of 45 degrees, sorry. And the most typical features of this transition now are nearly opposite to those found at low turbulence level. So we have absence of turbulent wedges, no any wedges, clear wedges are visible, but we have presence of strong intermittency, which was absent in low turbulence level case. And what we see on time traces, now I would like to say that this scenario of transition is much less studied than the case of low turbulence levels. What we see there, just prior to appearance of high frequency perturbations, we observe time trace like black one and spectrum also black one, frequency spectrum. But then suddenly very high amplitude flashes of high frequency disturbances appear. This is red time trace and red spectrum, frequency spectrum. We don't have any narrow peak now in spectrum, as in case of low turbulence level. The region of high frequency, amplification of high frequency disturbances is rather broad. However, this amplification is also very fast, extremely fast. And we have, it's broad because flashes of high frequency disturbances now are very much localized in time. That means they are broad in frequency spectrum. But we strongly believe, and we have some evidence of this, that the physical nature of this instability is the same, but it is essentially non-stationary one. So the secondary, high frequency secondary instability appears at different time instants and spatial locations where local amplitudes of traveling and steady disturbances exceed certain threshold. And here in this experiment, there is a very peculiar point, very important for experimentalists. We obtained all our enhanced turbulence level by means of turbulence generating grids, of course, because we have low turbulence wind tunnel. We put a grid at the inlet of the test section, and we enhance the freezing turbulence. But every grid has produced not only non-stationary disturbances, turbulence, but it produces also stationary disturbances, steady vortices, which amplitude can be very, very big. For instance, for this grid number G1, we have amplitude of this steady disturbances shown here. This is steady perturbation versus spanwise coordinate, less than around 0.1%. This amplitude is in fact immeasurable. It's impossible to measure it by hot wire anemometer in the usual way. To obtain these results, we applied several special measures, very peculiar measurements, and we measured it. For other grids, this modulation can be larger, for example, here 0.5%, but still on the border of accuracy of measurement by standard hot wire anemometer. And period, span-wise period is of course also different because we have different step of our wires, size of cells of the turbulence generating grid. And as a result, the scenario of transition on swap pin can be very much different. First, let's consider the case of grid G1. Now you see the same pictures. These are isocontours of stationary disturbances, isocontours of traveling disturbances, and high frequency disturbances. We can see that stationary disturbance is nearly absent now. We don't have any steady crossflow vortices. But we have traveling crossflow modes propagating downstream, and their character is, at least time averaged, is nearly span-wise uniform. No any turbulent wedges here is present. And intermittency appeared also, high-frequency disturbances associated with secondary instability appeared everywhere in span-wise direction. They are not localized. But if we replace grid G1 by grid G9, which has somewhat greater amplitude of steady disturbances and also significantly different span-wise scale, this is also important, then the picture, the scenario of transition is completely different. So you can see now large amplitudes of steady vortices. I want to emphasize that we have very smooth surface. Without grid, we don't have any significant stationary roughness, but surface roughness is very smooth. And in the previous case I showed here, this roughness was not able to produce any vortices. But now we see that steady vortices are present, and they are produced by grid, not by roughness. We also have very large amplitude traveling modes, which clearly interact with stationary vortices and span-wise modulated. And we have appearance of high-frequency secondary instability at some particular span-wise locations. And these are apexes of turbulent wedges. So we again have turbulent wedges. And this, I call this trap for experimentalists. So if you use turbulence generating grids to investigate influence of turbulence levels, you must very carefully measure properties of stationary disturbances produced by these grids. So this transition is produced by grids on smooth surface, grid G1, G9. And this is produced by grid G1 also on smooth surface. But the scenario of transition are completely different. And now let me say some words about the problem of transition prediction. The classical standard, starting from 1950s, method of transition prediction is n-factor method. N-factor is ratio of logarithm of amplitude at a certain x position divided by initial amplitude, which is taken at near the first branch of the neutral stability curve. And this method assumes that n-factor at transition is constant. So this is constant. For instance, if you believe that transition occurs when n-factor is equal to 4, then you calculate your amplification curve and find where it becomes equal to 4, and you assume that transition will start here. But I want to know that in this case, amplitude of disturbances at transition is not constant at all. And moreover, n-factors in the transition point vary in the region between 4 and 15. 4 is for for crossflow instability, as the swap means, and 15 for very good gliders for tone shifting waves. This means that amplification increases amplification factor is from 55 to 9 millions. and this factor is assumed to be constant. Therefore, of course, this is not a very satisfactory approach. And in 1997, Jeffrey Krauss suggested another method, which was called variable and factor approach. This approach is based on proved validity of linear stability and linear receptivity mechanisms. If they work, then it's very easy to obtain these formulas. These formulas assume linearity of receptivity and stability mechanisms, and also independence of receptivity coefficients of anything, I would say. Constancy of receptivity coefficient in certain range of variation of parameters. So n factor at transition is equal to a certain reference n factor minus logarithm of dimensional amplitude of surface roughness. This is for the case when transition is produced by stationary crossroad vortices excited by surface roughness. In another case, when transition is initiated by free stream turbulence and roughness doesn't play any significant role, this formula looks like this. So n factor at transition is equal to n factor reference 1 minus logarithm of free stream turbulence. Of course, this approach works only in the case when we have transition produced only by roughness only or by free stream turbulence only, separately. And this works. I want to show this plot from presentation by Jeffrey Crouch in Rio de Janeiro several years ago. So this is line correspond to this correlation of transitional location, variable and factor approach. And experimental points of transition location obtained in experiment by Radzetsi, Ribert, and Sarik, and in our experiment, green symbol, have quite good correlation. And factor changes here between 4 and 9, even more. It's not constant at all, but we have very good correlation with experiment. And in case of when the surface roughness is rather weak, so roughness height is below 5%, then we have more or less good correlation for traveling modes. For transition and factor of transition is equal to a reference and factor minus logarithm of free stream turbulence. The points obtained in our experiment for different kinds of grid and dashed line correspond to this formula. But in general case, when we have both modes, traveling and stationary, and both of them can be important, none of these formulas work. So we have quite more complicated picture, which cannot be described easily. So it's impossible to apply these formulas in this case. In fact, this n-factor approach can be improved if we take into account other mechanisms of receptivity, but still it remains invalid in case when we have mixture of stationary and traveling cross-flow instability modes. For this case, we need other criteria of transition beginning. They are required, and we performed a lot of experiments trying to find this criterion, a simple criterion, because we cannot measure instantaneous velocity gradients, which may be the main reason for the secondary instability. It's impossible to measure simply, but we need some very simple criteria. And we assume that this criteria we have to search. This might be one of amplitudes of perturbation. Here you can see amplitudes of stationary cross-flow vortices at transition, at the beginning of secondary instability. You can see that these amplitudes vary more than 1 order of magnitude, 30, 40 times. They are not constant at all. Then stationary disturbance, non-stationary disturbance amplitudes at transition. Again, the amplitudes are varying very much depending on surface roughness height and free stream turbulence level. But we found that if we introduce so-called combined amplitudes, this is just sum of instantaneous maximum deviations produced by stationary perturbations and non-stationary perturbations. This we call combined. These amplitudes show quite not bad constancy at the point where we have beginning of flow turbulization. And this amplitude is around 30%. So we found this criterion, and based on it, this universal criterion for swept-in boundary layer turbulization, some new transition prediction approaches are developing at present. I will show only one example. I don't have time anymore. So criterion of threshold combined amplitude is used in the amplitude method of transition prediction developed by Maxim Ustinov and Sagi. I show only one figure. It's obtained for LTL case, low turbulence level case, comparison of his calculated transition location black symbols with results obtained by Sarek with colleagues. No, a very good agreement. And several words about transition control. Unfortunately, I don't have time, so I just want to say that we can classify different means of transition control to subdivide into 4 different kinds. So direct modification of the base flow, like change of shape of the airfoil or angle of attack, modification of boundary layer conditions, flexible walls, for instance, method of disturbance superposition, interactive control, disturbance suppression via receptivity mechanism. This is a relatively new approach, so-called acoustic or vortex autodestruction. And also base flow modification by means of excitation of stable or weakly unstable disturbances. So I will slightly concentrate on this case. And I skip the history, description of history, but Bill Sarek suggested this approach for the case of 3-dimensional boundary layer. And recently, we found one more result related to this mechanism in our experiments, which I will show you briefly. This is 45 degrees swept wing. We performed visualization by infrared camera, and you can see here flow from right to left, laminar and turbulent, low turbulence level case. This is without control. This is with control by Sarek's method. We put here some patches, roughness elements, row, and you see the transition move downstream. And we wanted to understand how robust is this method with respect to acoustic excitation. We excited different acoustic waves and found no influence nearly. But in a certain rather narrow frequency range, we found that acoustics is able to stabilize the flow even more. So joint influence of these roughness elements and acoustic waves nearly remove turbulent flow from our model. Here we have trip device, 70% of course. And this was an unexpected result, which is still not explained by theoreticians. And one more case I will slightly describe is disturbance suppression via receptivity mechanism. Again, I think the first who found this mechanism was Kachanov many years ago. He found that putting some patches onto the surface, some roughness elements, is able to move transition downstream. And this was called auto-destruction. Similar result was obtained later in Stuttgart University, but for free-stream vortices, for predominant free-stream perturbations. And recently we obtained also this similar result for the distributed receptivity mechanism case, when we don't have any roughness elements, but we have waviness of the surface. And we excited stream biselongated free-stream vortices by vibrating wire with a non-uniformity here. The vortices look like this. And we put also waviness onto the surface, which was span-wise uniform. And scattering of these vortices onto the surface waviness was able to stabilize the flow. The matter is that in 2-dimensional boundary layer, free-stream vortices always propagate faster than instability modes. But in 3-dimensional boundary layer, this is not the case. So the free-stream vortices can propagate with the same speed. Here you can see stream-wise wave number versus span-wise wave number for one of frequencies. So free-stream vortices can propagate with the same speed as cross-flow instability waves, and this is resonant. But the most unstable modes are here at positive span-wise wave numbers, and the resonance here is possible only in presence of surface roughness. The resonant condition is shown here. And in this case, we can either suppress or enhance traveling instability modes by just presence of right roughness. And this is an example of the result. This is development of cross-flow instability mode downstream, amplitude versus chord-wise coordinate in absence of control, and this is in presence. So we are able to suppress growth of traveling modes just by putting roughness. And I come to the conclusions. So first, the linear stability and linear receptivity theories are applicable to description of cross-flow and tone shifting and TS modes in swept-in boundary layers. This is proved. Main sources of cross-flow vortices are roughness and stationary free-stream vortices. The second point was unknown previously, or weakly known, I would say. We showed this clearly. Main sources of traveling cross-flow waves are surface vibrations, first of all, but also free-stream turbulence, which can scatter on surface vibrations. Turbulization of three-dimensional laminar boundary layer always starts with localized high-frequency secondary instability, excluding cases of abrupt transition. Well, roughly speaking, if you put finger into the floor, this is a different scenario. Secondary instability appears when sum of maximum amplitudes of steady and unsteady cross-flow modes exceeds a certain threshold of about 30%. This is very important criteria. It works in a great number of cases. Weak surface non-uniformities are able to suppress both cross-flow vortices via base flow modification, as in Sarik's experiment, and cross-flow waves via mechanism of resonant distributed receptivity. Variable effector method of transition prediction works in cases of predominance of surface non-uniformities or predominance of free-stream vortices, but its applicability in cases of comparable amplitudes of steady and unsteady modes is questionable. And the final conclusion is that the amplitude methods of transition prediction based on 30% threshold of combined amplitudes are the most perspective ones at present, from my viewpoint. However, these approaches need complementary investigation in order to be used for real calculations of transition location. Thanks for your attention. Sorry for a delay.
No, that's fine. Well, let me thank you on behalf of everybody for a very stimulating talk. So if anyone wants to ask questions, if you raise your hand. But I mean, if I could say something in the meantime while people find how to raise their hands. This idea of a kind of combined amplitude method for transition prediction is much more appealing than the N factor method because it has some physics in it. It'd be nice to see how numerical calculations compare with this kind of 30% idea.
Yes, of course. If I understand your question, the amplitude method is clearly physically more reasonable than N factor or variable N factor, because it takes into account actually all most important mechanisms, receptivity, instability, and even can take into account some nonlinear saturation, for instance. But of course, this takes a lot of rather complicated calculations. So you must estimate receptivity, initial amplitudes of disturbances. You have to find the most important mechanism and perform some calculations. Then you must be able to perform calculations of instability correctly, and maybe also nonlinear things. I want to say that one of such methods has been developed by Maxim Ustinov. He had a talk in London, past IUTAM symposium on laminar turbulent transition, and talked about this method. And at present, this method is testing, comparing with experiments and so on. And hopefully it will work and it will be possible. He developed a very complicated method. I'm an experimentalist. It's difficult for me to estimate, how to say, its reliability and accuracy and so on. This will be shown, I think, by comparison experiment.
But it's much more positive than trying to add on extra terms in the n factor method to make it fit with reality, isn't it? I mean, it's a big step forward. That's my unbiased view. Su Shong has a question. Professor Wu?
Hi, Yury. Thank you
Hello.
for this very informative and stimulating talk. You mentioned this correlation with variable coefficient or variable n factor. So it's increased. So the main parameter is the height or the turbulence level.
Yes.
But surely these are not the only controlling, probably not even the most important parameters, because the shape and the location of roughness would change the transition position. And also intrinsically, it kind of contradicts to this separation of control. So using the right roughness, and you are going to delay transition, but according to this correlation, it always enhance cause earlier transition. So certainly there are a lot of.
I completely agree with you. Of course, you know, it's variable n factor approach is the next step after n factor approach. And if you compare them, you will clearly see that variable n factor approach is better because it takes into account receptivity. Very roughly, I agree. It assumes also that I say that this formula can be obtained if we assume that receptivity coefficient is linear, mechanism is linear, and the coefficient is independent of Reynolds number, of span-wise wave number, and so on.
Also the shape, right? Even in this case,
the shape, yes.
Shape,
the shape is spectrum. If you decompose it to Fourier space, you will get spectrum. Of course, spectrum is important, it's clear. If your span-wide scales are close to the most simplified cross-flow modes, then of course they will be important. If you have smaller scales or larger than more simplified cross-flow modes, they will be less important, it's clear. But this peculiarity, I would say, we can regard as a next step, you know, more detailed.
Okay, but by the way, this combined amplitude, how do you define it? You just take RMS of the fluctuation, the threshold of combined amplitude. How do you define?
So what we did, I understand the question. This is a formula which we use in a great number of our experiments. So I don't have plot here, but so the amplitude of stationary cross-flow vortices was just measured as you know, half of span-wise modulation of the mean flow produced by these vortices at the location where we have approximately maximum of cross-flow vortex amplitude. And traveling non-stationary perturbations were measured by hot wire, and we measured RMS amplitude of them. But then we had to estimate maximum instantaneous deviation when local high frequency instability can appear. Therefore, we multiplied this RMS value by a certain factor S. It's written S quartet, that means square root of S, but not, in fact, not. We found that this coefficient, empirically found, is varied between something like 2.5 and 1.5, I would say, or 1.4, depending on, of course, on spectrum of our perturbations. Again, spectrum is important, that's clear. But, you know, when we speak about rough engineering, simple methods of transition prediction, we are forced to simplify the problem. Otherwise, we can get nothing. So, therefore, the simplification is that we again assume that this factor, say 2.2, this is most typical value, and that's all. So, and we recalculate from RMS value to peak value when superposition of peaks of fluctuations and maximum values of mean velocity of oscillations, spatial oscillations, they produce strongest shear, high shear layers, where local high frequency secondary instability starts. This is the ideology. And it works. So we studied, I would say, 300 or 400 regimes with different surface roughness, different free stream turbulences, different kinds of turbulence. And I show here only part of points, but in reality, we have much more of them, and all of them concentrate around 30%.
With the same the coefficient, this weighting coefficient.
Yes, yes. Sometimes we corrected this coefficient, but we measured it experimentally. So we have time traces, and we have RMS, and we can estimate how large is this coefficient.
We have another question, Dr. Kato.
Yes,
I think you need to unmute your microphone, Dr. Kato. Yeah, that's.
Yeah.
Go ahead.
Actually, I have two questions, and one of them is related with the current discussion on this combined idea, and how can we physically understand the definition and the weighting of this combination if we simply assuming these two waves are completely independent? We usually taking the summation and square root, but it's not the case.
Yes.
It means, as you said, so local instantaneous amplitude is important for transition.
Yes, that's true.
That's correct.
Local in space and in time. But the physics is the following. First, we assume that steady, stationary cross-flow vortices and traveling cross-flow waves have the same physical nature. We have a lot of evidence of this. Just when frequency goes to zero, then vortices propagate slowly, 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 and then they stand still at a frequency equal to zero, and we have stationary cross-flow vortices. So they have the same physical nature. This is first point. Second point, that we performed a lot of measurements of both fluctuating non-stationary and stationary disturbances, and we always observe that maxima of oscillating of non-stationary disturbances nearly coincide with regions of, they are on a slope, on a strongest slope between maximum and minimum deviation of mean velocity in the span-wise direction. So the location, the span-wise location of maximum in non-stationary disturbances and maximum stationary disturbances are very close to each other. So they nearly coincide in space. And as in time, we just assume that there are some time instants when our non-stationary disturbances reach maximum values. And if this fluctuation coincide in space with maximum deviation of mean velocity, we have maximum instantaneous velocity gradients. Of course, the physics is clear. I showed several examples from experimental calculations. So high frequency secondary instability in 3D boundary layer is always sitting on the strongest velocity gradients. But in non-stationary case, these in velocity regions of strong velocity gradients appear for a short time in some spatial locations. And at these particular locations, we have flashes of high frequency perturbations. And this is the idea of the combined amplitude. We have superposition of stationary disturbance and traveling disturbance at some time instance and some spatial locations. And this superposition leads to beginning of turbulization of the flow through the mechanism of secondary instability.
Yeah, now it becomes much clearer. Thank you for your explanation. And another question is about the scenario of the transition for the enhanced turbulence level. And as far as I remembered, you said you believe that fundamental mechanism is similar to the other one. Also, the spectra is quite different.
Yeah.
I'm not really get it. Could you explain what remains the same mechanism?
So let me first to say that this is only a hypothesis.
Mm-hmm.
Unfortunately, this case, the physics of such secondary instability is very poorly studied experimentally,
Mm-hmm.
and as well as theoretically. So majority of people concentrated on cases of low turbulence level, stationary crossroad vortices as primary instability. And this is not very good studied. We have some plans of performing such detailed measurements for the case of enhanced turbulence level and to prove our hypothesis
Mm-hmm.
about similarity of mechanisms of high frequency secondary instability at low turbulence level case and in enhanced turbulence level case. But at the moment, I cannot prove this. We just see that everything looks similar. We have similar, very rapid rise of high frequency disturbances, but this rise appeared only for a short time on low frequency primary fluctuations, because this superposition of high shear layers produced by traveling and stationary disturbances is temporary, is localized in time and space.
Mm-hmm.
And locally we have flash of high frequency instability. This is our assumption. This is not
so
proof.
In the case, or if you apply the, for example,
Sorry, I can hear. Sound disappears.
Yeah, it's. Well, in the meantime, is there anyone else who wants to ask a question? If you want to just go ahead by unmuting the microphone, we can do it that way if you haven't worked out how to raise your hand. Do we have any more questions?
Okay, since we are at this right slide, may I jump in? Short question, sorry.
sorry, I'm frozen or.
Okay.
Could you hear me?
Yes, go ahead now. We have you back again.
Sorry, maybe it was my bad internet connection. But my question was, if we apply the temporal spectral analysis for this enhanced turbulence or level case, could we see the sharp or peak, which is similar in the low turbulence case, but this narrow peak is shifting with time? Is it your hypothesis or?
No, you know that for any Fourier analysis, we have a relationship like delta t multiplied by delta f is of order of unity.
Mm-hmm.
If we have localized in space, in time, flashes of high frequency disturbances, then of course Fourier analysis and temporal Fourier analysis will give broad spectrum of perturbations. So the amplitude of flashes either high or low and so on. Modulation in time means broadening in frequency spectrum. This is unavoidable. Therefore, in frequency spectrum, we have very broad high frequency disturbances, which also are amplified extremely quickly, similar to standard high frequency secondary instability. But of course, we can try to perform another kind of Fourier analysis. Just take one piece of time trace and with less, of course, frequency resolution, we can perform analysis of this, I would say, turbulent or high frequency part of time trace. And then I'm sure this the spectrum will be narrower. That's for sure. And I say you that we never studied this, never tried to analyze in detail. And this is, I would say, for future experiments.
Yeah, it will be interesting.
It's necessary to investigate this, and we would do this, but always not enough time, and you need some new project and so on. Financing.
I understand. Yeah, thank you for your great talk and explanation. Thank you so much.
Well, your time is getting on now. It's 15 minutes past the hour. So what I suggest is I thank Yury again for a great talk, and we'll just leave the meeting room open if people want to hang around and ask Yury informal questions. So thanks again, Yury. It was very
Thank you very much to everybody.